So now I just came across one of my old diagrams and figured I would cover this right now. So I wrote a lot of information about the circuit on there. So this is for absolute beginners. Once you have some experience with electronics, all of this should be common sense. But we have four parts really to this. We have the power supply. We have our load, our LED. The resistor could also be considered part of the load right there. And it's kind of the control. So we don't have a switch which turns it on and off. We have a resistor that limits current. One way that it controls current through the circuit, the resistor. This is a symbol for a multimeter right there, a drawing for a multimeter right there. And with the red LED, it's pretty bright with 15 milliamps of current. You're okay with 10 milliamps of current and so on. But 15 is a common target to shoot for red LEDs, in my opinion, at least for me. So we have some math down here. There is some numbers to be aware of. If you have a red LED, it's going to drop about 2 volts. So what that means is that out of the 9 volts in this case of our 9-volt battery, and be aware that batteries you have a higher voltage when they're fully charged and it goes down as they discharge. But if you buy an alkaline battery, which really aren't used much anymore, but we're gonna use it for the math here, then you know, the vast majority of the time you're gonna be close to 9 volts right there. And so we don't need exact voltages, exact currents and everything. Close is perfectly fine. It's good enough. The LED is going to be basically the same brightness the vast majority of the time till the battery's pretty much dead for the most part. So, in any case, it's going to drop about 2 volts. What that means, the current that flows through the circuit is set by the resistor. It's the voltage across the resistor divided by the resistance of the resistor. As I said before, the red LED is going to drop about 2 volts right there. So if we have 9 volts, math is really simple. That gives you, I wrote up there, 7 volts right there. So source voltage minus the voltage drop. That's talking about the LED right there, is the voltage that will go across the resistor. And I did the math down here. If you have 7 volts across it, so 9 from the supply, you drop 2 of those volts though from the red LED, 7 volts. Divided by 470 ohms, you got 0.01 and basically 5 right there. Amps of current. Again, you don't need precise numbers. This is, in the grand scale of things, exactly the same as 0.015 amps. Practically no difference. So, that is usually converted to milliamps, though. So, 0.015 amps, you do the math in amps. Usually you convert that to milliamps. So if you measure it with the meter, you're going to set the meter to the milliamp setting. And if it's an auto ranging, and then you'll get your number in milliamps. So it should be close to 15. And, you know, it'll probably be a little bit higher, a little bit lower for whatever reason. But it'll be close, which is good enough. So what that means is electrons are moving through, and that's basically counting how many electrons are moving per second, basically, to make things simple. Now, unfortunately, they didn't know about electrons early on in electronics, so they talked about current as if it was positive, moving to negative. But in any case, it's the counting of moving charge per time right there. So how much current's flowing through, just to make it simple. More current, brighter LED. Less current, dimmer LED. That's one way you can visualize it right there. So, we have another thing to talk about. When current is flowing, the heat is going to be generated. So, red LEDs have a pretty simple solution to that. Or these indicator LEDs right there, the little ones, they usually look like this. Sometimes that's not flat. And the cathode there is usually shorter, anode is usually longer, unless you cut them. And but when you buy them, that's usually how it is. You got to put it the right way for the LED to light up. Be aware of that. We're not going to dwell on that too much right now. So, at about 20 milliamps of current, it's going to get fairly hot, and you don't want to go above that. That's the maximum. You know, 15, 10 milliamps. It'll be cooler. It'll last longer. Just won't produce quite as much light. but 15 milliamps will probably produce close to as much light as 20 milliamps. 10 milliamps isn't even too bad. Other LEDs, you don't even need, other colors, you don't even need that much current. Be aware of that. So, how much current is flowing through the LED is going to determine how hot it gets because it maintains a certain voltage across it. When it comes to resistors, it's a bit more complicated. So, as voltage goes up, current goes up. And so, it doesn't maintain a steady voltage like LEDs do. And that's one way you can get a reference voltage. If you want circuitry that can tell if it goes above or below about 2 volts right there, you could use a red LED to set a reference voltage. Resistors, you can't do that. They take whatever voltage comes across them, and if you put multiple resistors in series, they'll actually divide up that voltage based on their resistance. But they pretty much just accept whatever voltage that ends up across them, and that will put the current through them. They are related. That's what we did right there with Ohm's law. When it comes to heat, though, you raise the voltage, that's going to also raise the current. The resistor is going to get hotter. So they get hot really quick as voltage goes up because current also goes up. You multiply them together. And so they create a lot more heat as voltage goes up. Very low voltage circuits, you don't have to worry about heat near as much as, medium to higher voltage circuits. So now we'll jump up here. As I said before, the LED, it's mostly producing light based on how much current's flowing through it. When it comes to power, that is pretty simple. The resistor, though, the power that it produces is heat right there, and it gets a bit more complex because it doesn't have a basically fixed voltage across it like LEDs do. As the voltage across the resistor goes up, current also goes up, and therefore it gets hot really quick because it's voltage times current as they both go up. If they double, then you'll have 4 times the power or 4 times the heat generation. You got to be aware of that. So 1 volt times 1 amp equals 1 watt. That's pretty simple math right there. But if you got 2 volts times 2 amps, that would be 4 watts. So 4 times as hot. Not too complicated a math. Main thing is when you do the math, do it in watts. Main thing is that most resistors that look like this, they're a certain size. It's pretty easy to tell. They're quarter watt resistors, which means their maximum wattage is 0.25 watts. Now, that's maximum. You don't want to do that all the time. And, maybe brief periods of time is okay. But for the most part, you want to stay about half of that or less. You can go as low as you want. That's perfectly fine. But about 0.125 watts, an eighth of a watt right there. The resistor will probably last forever, but if you get it close to its maximum wattage, good chance it will burn out. And so just be aware of that. And you don't have to worry about it getting too cold. That's no problem. Just try to stay below half if you can. So that comes with resistors that look like this. The higher wattage resistors are physically bigger, and sometimes they're made out of different material that helps dissipate the heat. Like very high wattage resistors might have a metal body so that the heat gets out a little bit better. So that's what the wattage means, the wattage rating, how well it can dissipate heat. And so the better it can dissipate heat, the more you can heat it up. So you just have to avoid whatever maximum temperature it melts down, or some of them will burn. So in any case, you do that math. We got 7 volts, about 15 milliamps of current, which is the same as 0.015 amps, but always do the math in amps. And so you got 0.105 watts in this particular circuit right there. Resistor is going to get quite warm. Don't grab the resistor while it's powering this. It'll hurt. It doesn't give you a serious burn or anything because these resistors are smaller, but a much larger value resistor. If you get to half of its wattage rating right there, physically large ones, and you grab them, you probably could get a serious burn. They get like that hot, but these little ones, they don't store enough heat to really give you a serious burn. I grab them all the time, and it hurts, but it's not super bad, these little ones. But the big ones, you could get a serious burn. So, yeah, low resistance points usually have a maximum current rating. And so yeah, that's because the LED, it takes about 2 volts before it will even conduct. And like 1 volt, if you put 1 volt across it, it's not going to let current go through. At about 1.5, it'll probably trickle a little bit of current. You'll see a little bit of light. But for the most part, you need close to 2 volts before current really flows through. At that point, if you try to raise the voltage, it's going to conduct, pretty close to like a wire. It's going to have 2 volts across it, but it won't limit current by itself. And that's why, in this case, we have a resistor. We could also use a current source, something that sets current, so that the current's steady even as the supply voltage changes. That's pretty straightforward. If you learn about current sources, you can apply them wherever. So the resistors are the ones where you really got to do like the math and stuff. You got the supply voltage, the load is dropping some of that voltage. What remains goes across the resistor. We just got one resistor. If we put another 470 ohm resistor in series with this, they would split it in half, the voltage. So one of them would have 3.5, the other one would have 3.5, and so on, right there. So single resistor is pretty straightforward. It's going to have the voltage across it. So semiconductors drop a certain amount of voltage, usually, not always, but if you hear voltage drop, and that means forward voltage, when it's forward bias, the way it's made to conduct. Reverse bias, if it's at RF, then that would mean the LED is in backwards, and I think they block up to 10 volts, maybe, or something, and then they'll have a breakdown voltage where they'll conduct, even though they're backwards. That destroys the LED. You don't want to do that with LEDs. There's other diodes for that kind of stuff. But if you put it in backwards, 9 volts, it's just not going to light up. And so make sure you put it in the right way, which is called forward bias. Anode more positive, cathode more negative. Remember that's longer lead more positive, shorter lead more negative. So I think we covered pretty much all the notes right there. Again, the LED, most of its power is for light. Doesn't really create a lot of heat unless you put too much current through it. Whereas the resistor, all of its power is heat generation. So be aware of that. The more that something provides, something useful, in this case like light, without producing heat, the more efficient it is. So, as we said, we just need 2 volts to light this LED. And therefore, 9 volts is kind of a lot of voltage. We have 7 volts where it is not producing light. 7 volts is going across the resistor right there and just turning into heat. So if we had a lower voltage source right there, then we would not be wasting so much power for heat. And so that power is a little bit complicated, but hopefully that makes sense right there. You want to limit as much waste heat as possible. So what we could do, we could get a voltage converter. And, there's a lot that take a higher voltage and will give you 5 volts. So, not quite half of what we got here, a little bit more than half, but, somewhat close. So, then we would have 3 volts across the resistor. Instead of 7, we could use a lower value resistor to get about 15 milliamps of current, and it would have less waste heat. So, that's one way you conserve power. Try to get the voltage as close to what the load needs, just a little bit more. And then limiting the current, you waste almost no power. Hopefully that makes sense. Now, when it comes to the meter, when you are measuring current, so you notice this is part of the circuit. Each one of these parts has two, an input and an output almost, but 2 points where it's connected to the circuit. So that would be a wire going to the positive supply, and then you might have other connectors, but hopefully they got no resistance. Basically it's a direct connection. And then other side resistor, direct connection to the anode of the LED, cathode, direct connection. Now we added a meter, so we could just go back to the battery. This will light up. I do that in a lot of my drawings and a lot of schematics. I don't usually include the meter very much. If you're going to measure the current though, which you should practice doing when you're beginning in electronics, that helps. Also for heat, you could buy a thermal camera if you're really serious about electronics, because they're not terribly cheap, but they help you learn a lot. You can see how hot components are getting. So that'll get you a better feel for wattage too. But definitely you want a multimeter that can measure voltage, current, and resistance. Usually they got a whole bunch more. And auto ranging is the most simple. You would just set it to milliamps there instead of amps. But any case, this is just a simple drawing. So we got that 15 milliamps. Current has to flow through the meter in order for it to measure it right there. There's other ones where you got like a little clamp or something. I don't have any. You could clamp the wire, and usually they're used for higher current, and they can sense the magnetic field, how big that is or however they do it, and get a reading there. But for smaller measurements like this, generally you got a multimeter. You open up the circuit, so maybe there's a switch that opens and closes. You could just put the meter across the switch. So even though the switch is open, the current will flow through the meter. The LED will turn on, but you'll be able to see how much current is flowing when you don't have the meter and the switch is closed. Hopefully that makes sense. But for current, you have to get the, or for measuring current, you have to get the current flowing through the meter for most of them in order to read it. If you want to measure the voltage, then you just, you got the circuit going, and you just put the probes on both sides of whatever you want to measure right there. So that's not really drawn on here, but I thought I would show that. So again, the meter provides practically no resistance. As I said before, we got the resistor there, and the voltage that the red LED doesn't drop versus the supply voltage right there goes across the resistor. Whatever resistance you got is going to take up some of that 7 volts that we're dealing with right here. So as I said before, if I had another 470 ohm resistor in series, each one would have 3.5 volts. So when you're measuring current, whatever you're measuring current with, you don't want it to provide any resistance. You want to keep it as low as possible, because whatever resistance it provides going to take away some of the current, some of the voltage across your current setting resistor in this case, and current through the whole circuit is going to go down, and you're going to get a lower current reading. So whatever reading you take of a circuit, you want to make sure that reading is close to what the circuit will be providing when the meter is not attached. So when the meter is measuring voltage, it has very high resistance because it does not want any current going through the meter, because then it will lower the voltage at a certain point. Hopefully that makes sense. But when it's measuring current, you want almost no resistance. So it should not really be heating up, especially at low currents right there. The ones that can measure like 10 amps of current, if you measure 10 amps current, it actually builds up heat because of how much current is flowing. So you got to take short current measurements. But at these lower measurements, you got almost no heat. So in any case, very long video, but I just came across this diagram. Thought I would explain it all. It's intended for absolute beginners, basically, with all the information I wrote on here. Once you get a little bit of practice, everything I just explained should just come to you really quickly right there. If you're not sure of, in this case, how much forward voltage or voltage drop you got with an LED, you just measure with the meter. You'll get it really quick. You can also look up a data sheet. And then when it comes to how hot a resistor is going to get, you do the formula right there. How hot power, voltage times current. Pretty straightforward. You don't have to do that a lot. It's just when you're working with a voltage that you're not used to, and then maybe a load, you're not used to how much current the load needs right there, and you've got a resistor setting that current. That's when you do this math. You make sure that whatever resistor you use, the current's not going to damage the, in this case, LED right there. So we want to stay below 20 milliamps, so 470 does that. But you also got to make sure the resistor doesn't get too hot. So you just use what I just talked about here. You got your supply voltage, whatever else is going to reduce voltage from that resistor, and then you do the math from there and make sure whatever the wattage rating is, generally you want to stay below half of that. So maximum is 0.25. And that goes with all kinds of circuits that you're going to work with in the future if you have not done so already. And it's not that complicated once you get used to it. It's pretty straightforward. You always know current needs to be limited, wattage needs to be limited. And if you want to measure it, in this case for current, just to verify things are going well, as I said before, you can get a thermal camera, make sure components aren't getting too hot, and you can also measure current. When the circuit's off, then you complete the circuit through the meter to turn it on, and you can verify that current is in the proper spot. So, in any case, hope you enjoyed. Make sure you check out one of the other videos I'm posting on the screen, and check out links down below. They all help out a lot. I'll see you in the next video.